Hello, everybody. Thank you so much for joining us today for this exploration into college physics. We are so excited to get started here in about a minute. As everyone gets situated, I would love to direct you to your Zoom window. Go ahead and navigate to the bottom. You'll see a little chat bubble. It looks like a little chat bubble icon from comic book. If you click that, you'll be able to send questions to today's presenters, send them to other people attending the webinar. So if you have any questions, please use that chat bubble to reach out to us. The most important thing we ask is that you click that little "To" section. It's got a blue, uh, something, I don't know what it says for you, but please make sure your "To" is set to everyone. That way, when we answer your questions either out loud or in the chat, we don't look like we're talking to ourselves. So go ahead and make sure that you are chatting everyone your questions. And it's kind of like a knowledge share. We want to see what other people are wondering, have conversations, build that community. It looks like we are just about at 1 o'clock, so I'll get started with some quick housekeeping items and then we'll get you off to today's presentation. If we could go to the next slide.
Sorry. There you go.
No, no worries. Awesome. You will get a recording of today's webinar. It usually takes us just a couple of days to get that edited, so the recording should be live within about 3 to 5 business days. Once it's edited, we will send you an email with that link. You will also get a link to today's resources folder. In that folder will be a certificate of attendance, today's presentation with clickable links, as well as some experiment files. I'm going to drop that folder in the chat in just a second here, so keep an eye on that. And as I mentioned, please use that chat to ask us questions. We are here and ready to help, but if we happen to miss anything, please reach out to us at physics@vernier.com, and we will get you taken care of. With that being said, I will pass you off to today's presenters. Keep an eye on that chat because I have a link coming to you soon, and enjoy. Thank you.
Thanks, Dylan. So my name's Josh. I'm a physics and engineering specialist here at Vernier. We're going to talk a little bit about first-year physics students and ways that we can, the tools that might be best for teaching them those introductory physics topics. And I've got Tom joining me today. Tom is also a physics and engineering specialist here at Vernier. He's going to be manning the chat. He'll be able to answer most questions, and those questions that are probably big enough and important enough, he'll just interrupt me and ask me those questions as well so that we can share it with everyone. Also with me today, you'll see in chat, is Dr. John Melville. He is on our college outreach team. So if you wanted to visit or demo some of the stuff we see I'll show today, John is the one that will hook you up with that. So I'm planning on I want to get to know you a little bit first, and I'm kind of planned my presentation today around 3 main topics, like teaching mechanics, teaching like circuits, and then also teaching optics. I felt like those 3 topics might cover what most students might go through in their first year of physics. Those first 2 semesters. My plan is that I'll demo some things along the way. We'll have time during it to answer some questions. There's also some time for Q&A at the end. Like I said, I want this to be a valuable experience for you. I'm grateful for your time today. So if you have questions, please post them in chat, and we're happy to help. I'm curious to know who I'm talking to. And so Dylan's going to post up a poll here in a sec, and I'm curious to know, are you already using Vernier stuff? Are you comfortable with our stuff, or are you just kind of dipping your toes into it? And also, where do you teach? This is, we college essentials, but we get a wide variety of instructors for these sorts of webinars. Even for something like this, we might get teachers that are AP or IB teachers, and for the most part, it all works. How you teach it might be a little bit different if you're teaching, first-year physics majors versus if you're teaching non-majors versus you're teaching high school students, that sort of thing. All right. Looks like just about everyone here already has some Vernier stuff and are also fairly familiar. That's great. I hope I can show you something new today then. Um, and mostly college, got at least one high school teacher. That's great. Like I said, the tools that we use that I'll show off today can be used at high school or college. How you'll use them will obviously be a little bit different, but I hope you all find something helpful here. The first thing I want to talk about is mechanics. There are lots of ways lots of tools that we make that you could use in any sort of mechanics investigation. You know, you want to teach motion, you want to talk about Newton's laws, conservation laws, those sorts of things. You may be familiar with motion detectors. We've been making motion detectors and photo gates for a long time. They're very versatile. You can measure all sorts of things with them. We have force sensors and those sorts of things. Kind of the latest version of all of our probes and sensors are what we call go direct. That means that rather than connecting the probe to an interface like a LabQuest Mini or a LabQuest interface or something like that and connecting that to your computer, they go directly to your device. So that means they'll connect either via Bluetooth wirelessly or via a USB cable. Um, I decided for mechanics, I decided to highlight our latest version of the cart and track system. So carts and tracks are real popular with physics teachers, especially these low friction carts that give you really clean, beautiful data. Our latest version includes the GoDirect sensor cart, and it's a cart like we've made in the past. We made a version, the first version we made were aluminum carts that were dark green. And then we made a version after that they were plastic carts that came in kind of a dark green or like a gray. And this latest version, they come in two colors, teal or chartreuse or green yellow, as some might say. And they actually include a fifth wheel that's encoded, and it's that fifth wheel that measures the motion of the cart. So with our previous versions of the cart and track system, you used a motion detector or a photo gate to measure the motion of the carts. With these GoDirect sensor carts, the carts themselves, are measuring their motion and transmitting that via Bluetooth to your device. You can buy the carts individually. So if you already have tracks and accessories and stuff like that, you can just buy the carts. If you buy it in a bundle, carts, track, and the accessories, you get what you kind of see here in the picture. It includes all sorts of things like these are hexagonal masses that kind of fit in these pockets on the top side. These hoop springs will connect to the built-in force sensor on the cart. Um, there are these tabs that go into the ends of the carts that you can swap out for like magnets or Velcro and that sort of thing for elastic and inelastic collisions. Um, I want to show you one activity in particular. I'm going to show you an impulse momentum activity that can be done just with everything that comes in the cart and track system. Most of our activities that we've written for our equipment for mechanics are going to show up in one of two places. We have kind of our core physics investigations lab book called Physics with Vernier. We also have one that's more geared towards calculus-based physics. So that's this advanced physics mechanics book. This is good for AP physics or as well as first-year physics students. Like I said, the advanced physics one is written with calculus, the idea that the students will be using calculus. I've included this impulse momentum activity in the Google Drive folder that Dylan shared a minute ago. So if you go to that Google Drive folder, you'll see this here, and you'll see that there are two files here. One is PWV, that stands for Physics with Vernier 19, Impulse Momentum. The other one is this PhysAM is Advanced Physics Mechanics number 10, also called Impulse. If you open those, you'll see that this is the student version of the activity. So it has the instructions on how it's going to work. It's a fairly simple activity. Because the GoDirect sensor cart has its own motion sensing, that fifth wheel, and it has a force sensor built into it. You can measure impulses to the cart itself as it bounces off the end stop. And then using our graphical analysis app, we can compare the actual impulse, the F delta t, to the change in momentum of the cart. All right, I'm going to switch views so you can see my cart and track. And go here. All right. So I've got here a track, the dynamics track that that comes with these GoDirect sensor carts. This is the sensor cart itself. You can see this is that fifth wheel. It's I don't know how well you can see on the video here, but it's kind of shiny, and it's actually there are tiny little stripes there. That's the encoding there. And as it moves, there's a little LED that watches the motion of those stripes. That's how it figures out how far it's traveled. You'll see that it's like spring-loaded. That's because it's designed so it can run off-track. You could just run it on a tabletop, and it would still sense its motion. It's kind of spring-loaded there, so it always keeps in contact with the ground. Otherwise, it's like most of our carts in the sense that it's got a plunger on one end here that you can use to launch it. These are those tabs I was mentioning. These are blank tabs, but you can swap these out for magnets. You can also it comes with these Velcro dots that you can put on here for inelastic collisions. At the other end of the cart, there is a load cell that's built into here. If you have our dual range force sensor or our GoDirect force and acceleration sensor, it's the same load cell. So it's got a plus or minus 50 Newton range. Right now I have a hoop spring attached to it. If you buy the cart and track system to kit together, you get two hoop springs. One's stiffer and one is softer, On the top side here, this is where there's those places to put in like these hexagonal masses to change the mass of the cart. So what I'm going to do is I want to connect to my cart, and I'm just going to have it bounce off my end stop here, and I'm going to measure both its motion and the force, the force interaction at the end here as it bounces off the end there. I'm going to first turn on my cart. It's got this little red light, means that it's on, but it's not yet connected to anything as far as like Bluetooth or a device or anything like that. I'm going to put that on here. And then in graphical analysis, I'm going to connect to my cart. It'll just show up here. I'm on a PC right now, and this is graphical analysis for Windows. And this cart-y. This is mine. You can tell it's mine by this unique ID number. This is the same as what's on the cart itself. So I'm going to hit connect. And by default, it's set up to measure position. I also want to measure force. So I'm going to open this menu here, and I can turn on the force sensor as well. You'll notice there is also a 3-axis accelerometer built into it. So if you wanted to hang this cart from a ring stand and have it bounce up and down on a spring, you could measure force and acceleration at the same time. If you wanted to swing it around your head, you could do that too. I don't know that I'd recommend it. I'm going to hit done. I've got here 3 graphs: force on the top, position, and velocity. I'm going to adjust a couple of things here so it's a little easier for you to see. The first thing I'm going to do is I'm going to change so I only have 2 graphs. Since this is an impulse momentum experiment, I'm really most interested in force, and I've got force on top here. I'm going to change this to velocity though. So I'm going to turn off position and turn on velocity here. And then I'm going to make it a little bit bigger. I'll scale it up a little bit bigger so it's a little easier for you to see the labels here. So I've got force, I've got velocity graphs here. That's just going to collect data versus time. I can see a few things here, like I've got a live readout for my position and the force in the lower right-hand corner. I'm going to make this force here. I want to zero that out because right now it's not touching anything. I'm going to click on that and I'm going to zero it so that I don't have that offset there. And as far as position goes, you can see that on the top of the cart, there is an arrow. And if you move in the direction of that arrow, position will increase. And if you move away from in the opposite direction, it's going to decrease. That's also like obviously going to be the same for velocity and acceleration. I'm gonna call, it doesn't really, because I'm just looking at velocity, it doesn't really matter where I call 0. So I'm just going to call where I am right now 0. I'll do the same thing and choose 0. And okay, so at this point, I'm pretty much ready to go. I'm going to hit collect, and then I'm going to push the cart, and then it's going to bounce off the end stop, and then come back, and then I'm going to catch it when it gets back to about 0 or so. So here we go. Collect, let it go, and then catch it. And you can see it recorded data for about 5 seconds. I'm going to auto scale here so it looks it's a little bit bigger. You can see that. And in this activity, in either the physics with Vernier or the advanced physics mechanics book, students are really looking for two features on this graph here. They know that at the beginning here it was at rest, and as I pressed it on the cart, it got up to speed, and then was rolling along at about a constant speed until it hit the end stop. And I can kind of tell that this is where the action happens, right? This is where I get a force. I can see it gets bigger, and then it tapers off while it's in contact with it. And it's during this time that the force of the end stop is pushing on the cart, applying an impulse. And that's also when the velocity of the cart is changing. So this is kind of where all the action is happening. And typically, what we want to do is we want to compare the impulse, the area under this curve, with the change in momentum shown by this change in velocity here. You can view an integral. That's kind of like what you would do typically in a calculus-based class. It's really easy to measure that integral. Does a graphical analysis, does a numerical integral on this. If you're not teaching calculus-based, say it's a class for non-majors, you might select this region and then instead choose statistics. If you choose statistics, you get an average value for that same time interval. And then you can multiply that average value by the change in time, which is this delta x here, and you get the same value, right? That's kind of like your average force over that time interval gives you this, estimates about the same. Once you know what that impulse, the impulse provided by the end stop was, you can compare that to what was the velocity just before it hit the end stop? What is the velocity just after it hits the end stop? Multiply those two velocities by the mass of the cart, and you can compare those two. And no surprise to us, those two values will end up very, very close to each other. I really like this experiment because it really shows off a lot of the versatility of the sensor cart. If you, obviously this is a momentum impulse experiment. A lot of times you'll do, let's say, a conservation of momentum experiment where you'll have two carts bouncing off each other. You can do that really easily with these sensor carts. When you do conservation of energy laws, you might tip your track up, so you have the cart launching it up a track, an inclined track, and you can measure the change in gravitational potential energy and the change in kinetic energy. Likewise, you could, because I have a force sensor and a position sensor all in one here, you could measure the spring rate of this hoop spring, and then use that to calculate the elastic potential energy stored in the spring, and compare that to the kinetic energy it gains as it leaves the end stop like that. They're just, these carts and tracks, when you first look at it, you're kind of like, oh, that's a little pricey, for the two carts and the track and all that stuff. But when you realize that you could do a whole semester of mechanics experiments using just this one tool, it actually turns out to be pretty economical, All right. Let me see here. Let me look at my notes real quick to make sure I haven't forgotten anything. Okay. All right. It doesn't look like there are any questions in chat. Like I mentioned before, if you've got questions as we kind of go through these things, feel free, please, to ask those questions, and Tom will interrupt me for the important ones or the bigger ones, and we'll go from there. I mentioned before that there are lots of ways to measure motion. This is kind of our GoDirect motion detector. It uses that same transducer that our other motion detectors and the green ones we've made in the past. This one's it's the same way though. It's USB and wireless, the way all of our GoDirect sensors are. So if you're going to mount it on a ceiling, it makes it really easy because it's going to be no wires. This is our GoDirect photo gate. It also is really good at measuring motion. The GoDirect version is actually a double gate in the sense that there are actually two photo gate beams here. The reason is the reason why we doubled it like that was because we found that nearly everybody the first thing they wanted to do with the photo gate was measure a speed. Like a matchbox car or marbles rolling through here, they wanted to measure speed. And by using a double gate like that, it's really easy. You know that the spacing between the two gates is 2 centimeters. And so all it has to do is time when the beams are broken. So that's this, but you could still use this like a traditional photo gate in the sense that you could also put it under a pendulum and measure the pendulum period. You could drop a picket fence through air to measure the acceleration due to gravity. It does all those things as well, but it just makes it one step easier by having it as a double. This is our force and acceleration sensor. So it's like our dual range force sensor. It's designed to measure forces, but it also has a 3-axis accelerometer and 3-axis gyro built into it. So you could have this bobbing on a spring or whatever and measure force and acceleration at the same time. You can swing it around your head. There are lots of things you can do just with this. If you have an older version of our force and tracks and you want to do the same sort of impulse momentum experiment, you can use this in combination with a motion detector or a photo gate. This will measure the force. You can mount this to the top of your carts and have it bounce off an end stop like that. Then use a motion detector or a photo gate to measure its speed. The other things here, these are those masses. I'll point out is we have a number of accessories for the sensor cart. One of them is this. It's just a fan that you can mount to the top of your cart and apply a constant force that way. We did another webinar about that last year, and if you have questions about that, we can point you there. All right, I'm going to change gears a little bit here and switch to second year or second semester typically, and talk a little bit about teaching circuits. I really love teaching circuits. There's this danger that when you teach physics, you're just going to end up teaching an applied math class, and it's not just an applied math class. It's like real life. So one of the things I really love about circuits is that it's such a tangible, hands-on way to look at these physics principles. We make a variety of tools to study circuits, to investigate circuits. The core of that is our circuit board and our voltage and current probes. The circuit board is kind of like an all-in-one sort of thing. It's got a whole bunch of components, resistors, an LED, a buzzer, some capacitors, those sorts of things, some switches, all built into one. It's all on one board so that you don't have to worry about stuff wandering away. Each of those components you can connect to it just by these posts and then alligator clips. You use the alligator clips to create your circuits. Likewise, our voltage and current probes you can kind of clip to these posts to be able to measure aspects of the circuit that you're investigating. Our circuit board you can power via AA batteries or an external power supply, or if you have our LabQuest interfaces, there's actually a little port on the lower right corner here where you can just plug in a LabQuest power supply. That's actually 5 volts like that. That's pretty nice. I actually tend to use that the most, just mainly because I always have a LabQuest power supply at my desk, and that's how I'm going to do it today as well. Some things I might point out, additional things that might be helpful for teaching circuits. we have a little breadboard kit. There's a spot in the lower right corner of the um, of the of the circuit board where you can stick a little breadboard, and it comes with additional components like transistors and uh, uh, tricolor LEDs and a photoresistor. I'll show a little bit of that here in a minute. And then there's also, we have a frequency generator power amplifier you can use to drive AC circuits on this as well. So for things like RC and RLC circuits, you can use the same circuit board, just putting in an AC signal. I included two activities around circuits, one from Physics with Vernier, one from our Advanced Physics Beyond Mechanics book. This is Beyond Mechanics. It's kind of like the second semester college, lab book, and they are both. You'll find them in the same Google Drive folder. Both of them are around capacitors. So one is I'll demo this one here in a minute. This capacitors activity from Physics with Vernier. You'll see that there's a similar activity from the Beyond Mechanics book called Capacitors and Inductors. There is on the circuit board, there is an inductor here, and then also like this iron core that you can stick inside the inductor to change its inductance. All right, I'm going to swap out my track here for my circuit board. Just a sec. I'm going to change what I'm sharing here. Okay, I'm going to move this. This guy. Okay. Going to change. Okay, so here's our circuit board. You'll see I've got a circuit set up here right now. This is the circuit from that capacitors lab. I'll start with talking about power. So I've got 4 AA batteries here. You can choose to power it by these 4 AA batteries. And you can choose, how many batteries you want to actually include. This terminal over here is for an external power supply. So if you had like a big benchtop power supply, you could connect it in here, either using these little wired connectors, or you can use these same posts. Likewise, this little port on the bottom here, I have a LabQuest power supply plugged in there, and I actually have it set right now. This little selector switch allows you to choose between batteries, external power, or the LabQuest power supply. Regardless of which one you choose, the way the circuit board is wired up is this first post up here is always, your high side of your battery, of your power supply, and this last post is also the low side of your power supply. So right now, with it connected to the LabQuest power supply and selected there, this is set to 5 volts and this is set to 0 volts. And then I use these alligator clips to complete my circuit. The circuit that I've got here is the one that's in that Physics with Vernier activity. Basically, I've got power coming to a switch here, and if I have it switched in one position, it will charge an RC circuit. So I can come here to a 100K resistor, and then from the 100K resistor to this 10 microfarad capacitor, and then from there back to ground. If I move the switch to the other position, then it closes that circuit and it discharges that capacitor. So in one position it charges, in the other position it discharges. Across my capacitor here, I have my GoDirect voltage connected. I'm going to connect to this so I can get a reading, and then I'll collect some data of the charging, discharging. You can use these voltage and current probes just like you would a multimeter, but the advantage to the current and voltage probes is that you can log data versus time. So then you can it's very easy to create these charging and discharging curves from you can collect that data itself. I'm going to go here and connect to my voltage probe. Here it is. And it by default is set to a kind of a 20-volt range. You can also measure much smaller voltages by changing it to a 1-volt range. And I have the resistor and capacitor, so a 100K resistor and a 10 microfarad capacitor were chosen such that I end up with a time constant that is like a good, reasonable one to measure. And so I'm going to have like this 10 seconds of data collection is pretty good, but it's 10 samples per second is kind of a slow data collection rate for this sort of thing. So I'm going to change this, and I'm going to change it to, say, 200 samples per second. And in the activity, it has students set up triggering so that it doesn't actually start collecting data until you trigger, until that you charge or discharge the capacitor. I'm not going to worry about that right now. I do want to charge my capacitor, though, so I'm going to flip the switch here. And I can see in the lower right-hand corner that the charge across the capacitor is increasing, and it reaches about 5 volts. That's what I'm getting from my LabQuest power supply. And so now that at this point the capacitor is charged up, I'm going to hit collect, and then I'm going to flip this switch and have it discharge. And graphical analysis is going to collect that discharge data. So I'm going to hit collect here, and then I'm going to discharge, and there it goes. And you can see it reaches 0 pretty quickly there. Like I said, we chose the resistor value and the capacitor value such that you get this nice long time constant. I'm going to make this a little bit bigger. You can kind of see that LabQuest power supply is really convenient. It is kind of noisy. It's just connected to, it's not the best power supply in the world, so it's a little noisy. But typically for something like this, I'm interested in knowing I want to measure that time constant. I want to compare it to R times C. And so the way that you do that is by selecting the region of the graph here, this nice discharge curve, and then I'm going to apply a curve fit to it. And if I wanted, I'm using the pro version of graphical analysis right now. I could actually plug in I could write in the mathematical form. If I choose just from the drop-down menu, though, one of the options is the natural exponent. And if I choose that, I know this is kind of the form that I want. It matches it pretty darn well. And I know that this constant C here, this fitting parameter C, is actually 1 over the time constant, right? So if I inverse that, it's going to be somewhere around 10. That kind of makes sense. I want to show you, so this is just the standard circuit board with the voltage probe. This is an activity you could do just with that particular thing. I want to show you if you do decide to get the breadboard kit, the optional breadboard kit. This is discharged. I'm going to swap that out for just so you can see what that's like. So this is when I say the breadboard kit. It comes with this little baby breadboard, so cute. And it comes with all these with additional components that are designed for a breadboard. So just the kind of electronic components you used to get from, Radio Shack, and nowadays you probably get from DigiKey or MakeMaster Car or somebody like that. Anyway, I set up a circuit here, a simple circuit that uses this photoresistor here that I've got mounted as kind of a trigger to turn on and off this red LED here. I'm going to turn off some lights here so you can see it a little bit easier. But this is, if you were to teach like a intro to digital electronics, this would be something this is the kind of activity or the kind of circuit you might build with your students. I have, from the high side here, I've connected a 47 kilo ohm resistor that's connected in series with this photoresistor. The photoresistor varies usually somewhere, depending on how bright it is, from 10 ohms or 10 kilo ohms to 100 kilo ohms. And from there back to ground. That voltage divider circuit there, the middle leg of that is connected to the base of an NPN transistor here. I don't know how well you can see that. That's this guy right here. So when that intermediate voltage there in the divider rises high enough, then it allows current to flow through another branch of the circuit and turn on this little LED right here. So I'll see you can see that's the LED there, and as I put my finger over my photoresistor, it turns on, just kind of like a garden lamp would, or, like a street light or something like that. But it's a real simple circuit. It's really, it's pretty easy to put together, and it is an easy way to talk about some of those more advanced circuit, principles. You talk about voltage divider circuits or circuit design and that sort of thing. And it makes it real easy to use the circuit board that you're already using and just add a bit more functionality with a breadboard like this. Little baby steps into actual digital electronics and that sort of thing. Let me think. All right. Yeah, it looks there's a quick discussion here in the chat about calculated columns, calculating your own derivative. And yes, both graphical analysis and Logger Pro allow you to do your own, to create your own calculated columns that include derivatives. If you're used to Logger Pro, you'll find that Graphical Analysis Pro, the calculated column options are very similar and will work just the same way. All right, we've got a few minutes left. I want to talk one last thing. I want to show kind of like our optics expansion kit here. We call this the optics expansion kit because it makes use of the tracks that you already have. Well, you probably already have. I'm going to move my circuit boards out of the way so that I can show you a little bit more about what these are. You'll see that there are these pieces that you just attach that clip to the sides of the dynamics track. So in this particular image here, you can see this in the upper right corner here. This is a light source. You'll use that nearly all the time. This is a screen that you can use to catch an image. These three pieces here are actual lenses. So there's a 10 centimeter converging lens, a 20 centimeter converging lens, and a 15 centimeter diverging lens. This other piece here. It has a number of different apertures that you can use to put in your optics system here to kind of see if I change the aperture, if the light has to pass through an open window like this or a half closed window, how does that change what I see? Likewise, this piece right here with these additional other pieces, this kind of acts as like a stage where you can mount like a light sensor. We have our GoDirect version of the light sensor is GoDirect Light and Color, and you can mount it on here. So you could do like, one of the activities that we have is light brightness and distance, where you look at it, where you see students measure the inverse square law for a light intensity. This is the optics expansion kit. We have a whole bunch of additional pieces you can add to this to investigate other aspects of light. So there's like a mirror set. So you can look at the images formed by mirrors. Likewise, a color mixing set that comes with like a RGB LED light source, so you can turn on and off the different colors to see how they mix. There's a polarizer analyzer kit, which allows you to look at, it comes with two polarizing filters that you can rotate independent of each other to look at like Malice's law. And then there's also a diffraction apparatus, which comes with a laser and a series of diffraction gratings, and then a high precision light intensity or light sensor and a displacement sensor, so you can measure you can recreate the bands of light and dark spots and measure those as well. I'm going to switch my cameras over here so I can show you a little bit about kind of how this all really is supposed to work together. Make this a little bit bigger. Okay, I'm going to switch screen I'm sharing. All right. So I've got here, this is kind of like the screen where it's going to, I'm going to catch an image. I'll move that up here so it's a little easier to see. I'm going to put on my power source, my power supply. This is my light source. I'm going to plug this guy in, and this is, you probably can't see unless I hold it just right, but there's a couple of different options here. This is just straight white. You can see it's just a circular opening here. You can also get a pair of slits, a pair of lines here. Here is one that's like an L, and then you also have like the number 4. And that's just, the L and the number 4 are there because it's a little easier for students to identify whether an image is upright or inverted, if you have some shape to it. So I'm going to plug that in. I'm going to have that here. So I got my light source here. I've got a screen here to catch the image here, and I'm going to put a lens in the middle here. So I've got, because I looked at this earlier, and I figured out this is our 10 centimeter convex lens. I'm just going to put this in between, and then because I'm using my dynamics track that I've used for other things, it has graduations along the edge here, so it's really easy to measure the distance from the source to the lens, and the distance from the lens to the image. And I'm just going to move this guy. As I move it back and forth, you can kind of see that my image comes in and out of focus, and I'm thinking it's probably right around there that it is most focused. And I can see I had it set to the 4, and it shows up here inverted, which is, well, there's no surprises there. I'm going to change this just so you can kind of see what it's like. There's that, the L also ends up inverted. My 2 slits, I don't know if you can tell that there are 2 slits there too. They're smaller than they were on the source here. And then this is just a single point of light. So we have the optics expansion kit comes with, this is a 10 centimeter convex lens. There's also a 20 centimeter convex lens. And I want to say it's 15 diverging lens, And you can actually use all those pieces together to make a telescope, which is kind of fun as well. I mentioned before that you can swap out pieces here. One of the pieces that you can swap out is if you wanted to do like an inverse square law experiment, you can take out these lenses, the lens and the screen, and instead mount this is our Go Direct light and color sensor. It's got a number of different sensors on the front here, but the one that you use most often is light intensity. It has an RGB sensor and a UVA, UVB sensor. You can mount this on here and line it up with your light source. Usually you'd have it set to this one. And then you can measure, the brightness of the light at different lengths, distances from your light source, and measure that inverse square law. Another thing that you might do, one of the other options I mentioned before was a polarizer analyzer accessory. That's like this guy. There's actually a polarizing lens in there, and you can see there's this little white mark here, kind of tells you at what angle that polarizing lens is oriented. So as I turn it on the back here, I can measure that angle. Often you'll use these in pairs. So you can put one down and measure the light intensity on the other side. And if you want, you can put a second down likewise in here. And now that I have 2, I can measure, light transmitting through the first one, and through the second one, I can measure that light intensity, the resulting light intensity. This second one actually we have a rotary motion sensor. This is one of our older LabQuest rotary motion sensor mounted to it. So it measures the angle from just from that sensor. And so you can do a real slick Malice's law, investigation just by rotating this guy. It measures the angle from the second polarizer, and then in graphical analysis you get this nice, beautiful cosine curve. Anyway, that is our optics expansion kit and accessories. Another way, a real hands-on way for students to engage with the principles that they're learning in their second semester physics course there. All right. Tom, did I miss anything? Feel like
I don't think so. You seem to be hitting all the main points. Like you said, we had a little discussion in chat about calculated columns, but otherwise nothing showed up here. If you have questions though, fire them in real quick or give us a call or drop an email to either collegeoutreach@vernier.com or physics@vernier.com, and we'll get back to you as soon as we can.
We're happy to do it. A big part of what Tom and I do is answering questions like that. So if you ever have questions about the Vernier equipment that you have, or you want to supplement what you have, we're happy to walk you through that process. I'll make one last note here. Today I used our graphical analysis software. I used the Pro version. I don't know that I used actually any of the features that I showed. I don't think any of them were specifically Pro, that you had to have graphical analysis Pro to do. But kind of graphical analysis is our general purpose data collection and analysis app. We make versions for Windows, Mac, iOS, Android, and Chrome. It works with all of our old sensors as well as all the newest stuff. There is a version now that if you're on a Chromebook, you have to use that, or it just runs within the Chrome browser, graphicalanalysis.app. In fact, if I go here and just I'm on Chrome right now, and just plug this in, it just loads the app within the Chrome browser. That can be really handy. There's a free version that most people are using. There's a pro licensed version that physics teachers really like, because I really like to be able to, when I do a calculated columns, I want to take velocity data and make it into kinetic energy data. I really like being able to type in 1/2 times the mass times my velocity squared. I like being able to reinforce that relationship, and Pro allows you to do that. It has a number of more advanced analysis features, as well as options for sharing data across the internet with your students or within lab groups, as well as there's a lot of video and lab data that's been synced together that you have access to, that makes it easy, especially for makeup work or for students that miss a lab activity. They can still do the analysis portion just because we have sample data and videos for them already to use. If you're a long-time Vernier customer and you're used to Logger Pro, and you know that you're going to have to transition to graphical analysis sometime in the future, we put together a web page to help with that. That's posted here. I encourage you to check that out. And if you want to try Graphical Analysis Pro for a month for free, we have free trial licenses like that. All right. I don't know. I don't think there are any. I didn't see any additional questions that we needed to address here. Yeah, John makes the point that if you email physics@vernier.com, that's going to go to Tom or me or Fran or Verl. We're all the physics specialists here, and we're happy to help you out. All right, I think Dylan's now going to do a giveaway.
Absolutely. We are giving away a GoDirect voltage sensor, and I've entered everyone who attended today's webinar into a random name generator, and today's winner is Peter L. So congratulations, Peter. I'm going to email you in just a moment to get some shipping information from you. And so keep an eye out for an email coming from someone at vernier.com. So congratulations, and thank you.
Thank you again, everyone. It's great to have you here. We have been trying to do webinars like this about once a month. We're doing our next physics one, I think, might be on the other side of spring break, about waves and wave phenomenon. So we'll hope to see you then.
All right. Thanks, everyone. Have a great rest of your day.